Quantum computing's future daily use. The end of privacy and the rise of quantum intelligence. Everything you currently believe is private is living on borrowed time. Your bank account details, your medical records, your passwords, your personal conversations. For decades, modern civilization has relied on a simple assumption that certain mathematical problems are so difficult that no computer could realistically solve them. That assumption became the foundation of digital trust. It protects global finance, government communications, corporate secrets, and nearly every online interaction we make. But that foundation is beginning to crack. A new form of computation is emerging from the strange and counterintuitive world of quantum physics. Unlike every computer that has shaped the modern era, quantum machines don't simply process information faster. They operate according to an entirely different set of rules. And those rules have the potential to transform everything. The transition to quantum computing won't just create more powerful technology. It will reshape economics, cybersecurity, logistics, artificial intelligence, medicine, and perhaps most significantly, our relationship with privacy itself. The age of silicon is approaching its limits. The age of qubits is beginning. For more than half a century, technological progress followed a familiar pattern. Engineers made transistors smaller, processors faster, and devices more efficient. Each generation delivered more computing power than the last, fueling the rise of the internet, smartphones, cloud computing, and artificial intelligence. But we are now approaching a fundamental boundary. Modern silicon chips are being pushed towards physical limits that cannot be overcome simply through better engineering. As components shrink to atomic scales, they generate more heat, become increasingly unstable, and encounter the unavoidable laws of quantum mechanics. Ironically, the very phenomenon that threatens traditional computing may become the key to its successor. Instead of resisting quantum behavior, researchers are learning how to harness it. Traditional computers rely on bits, the familiar ones and zeros that form the language of the digital world. Every calculation, image, video, and application ultimately reduces to these binary states. Quantum computers use something radically different: qubits. While a conventional bit must be either 1 or 0, a qubit can exist in multiple states simultaneously through a phenomenon known as superposition. Imagine attempting to navigate a maze. A traditional computer explores one path after another, eliminating incorrect routes until it finds a solution. A quantum system can evaluate vast numbers of possibilities at the same time, dramatically changing how certain problems are approached. This isn't simply a faster version of the computers we already have. It's a fundamentally different model of computation. And that difference is powerful enough to challenge some of the assumptions on which the modern digital world was built. Nowhere is that challenge more significant than in cybersecurity. Most people never think about encryption, yet it protects nearly every aspect of modern life. Online banking, government communications, medical records, business transactions, and personal messages all depend on cryptographic systems that were designed for a world dominated by classical computers. Today's encryption standards rely on mathematical problems that would take conventional machines thousands or even millions of years to solve. Quantum computers change that equation. Using specialized algorithms such as Shor's algorithm, future quantum systems could solve certain cryptographic problems dramatically faster than traditional computers, potentially rendering many existing security methods obsolete. What was once considered practically impossible suddenly becomes achievable. That's why governments, technology companies, and financial institutions around the world are investing heavily in post-quantum cryptography. The race isn't simply about building quantum computers. It's also about protecting society before those computers become powerful enough to challenge current security systems. Yet an even greater concern is already unfolding. Security experts call it harvest now, decrypt later. Sensitive data is being collected and stored today, not because it can be read immediately, but because it may become accessible in the future when quantum capabilities mature. Information stolen now could become transparent years later. In many ways, the quantum age has already begun. But while cybersecurity dominates the headlines, quantum computing's greatest impact may come from the systems we rarely notice. Every day, millions of shipping containers move across oceans, railways, roads, and air routes. Behind every delivery lies an immense optimization problem involving weather, fuel costs, traffic conditions, inventory levels, customer demand, and countless other variables. Traditional systems can analyze these factors, but only within practical limits. Quantum optimization offers something entirely different. By evaluating vast combinations simultaneously, future quantum systems could identify solutions that would take conventional computers weeks or even months to discover. The result would be faster supply chains, lower costs, reduced emissions, and a more efficient global economy. The same principle extends to aviation. Flight routes could be adjusted dynamically. Fuel consumption could be minimized. Delays could be anticipated and prevented before they occur. Transportation networks would no longer merely react to events. They would continuously adapt in real time. Cities themselves could become intelligent systems. Traffic signals would coordinate dynamically. Public transport networks would optimize continuously. Emergency services would be rerouted instantly around developing congestion. Urban gridlock wouldn't simply be managed. It could be predicted and avoided altogether. Yet some of the most extraordinary breakthroughs may happen on a scale invisible to the human eye. Chemistry itself operates according to quantum principles. Atoms and molecules interact through the same laws that govern quantum computers. Ironically, this makes chemistry extremely difficult for conventional computers to simulate accurately. Quantum computers are different. Because they operate according to similar principles, they can model molecular behavior far more naturally. This could revolutionize material science. Scientists may discover new battery technologies capable of storing far more energy than today's systems. Carbon capture materials could become dramatically more efficient. New medicines could be developed faster and with greater precision. Solar technologies could reach efficiencies previously thought impossible. Instead of spending years conducting physical experiments, researchers could simulate countless possibilities before entering the laboratory. Entire industries may accelerate beyond recognition. And then there is artificial intelligence. Today's AI systems are impressive, but they remain constrained by computational limitations. As models grow larger, they require enormous amounts of energy, processing power, and time. Quantum-enhanced AI could fundamentally alter those constraints. Future systems may analyze vast solution spaces more efficiently, uncover patterns that remain hidden to classical systems, and tackle optimization problems on an unprecedented scale. The result may not simply be smarter artificial intelligence. It may be a different category of intelligence altogether. This shift will inevitably transform the workforce. Throughout history, technological revolutions have changed the nature of work rather than eliminating it entirely. Agriculture gave way to industry. Industry gave way to information economies. The quantum era may create another transition. Routine administrative work, repetitive analysis, and basic coding tasks are likely to become increasingly automated. At the same time, entirely new professions will emerge: quantum engineers, quantum software architects, quantum cybersecurity specialists, quantum infrastructure designers, quantum ethics advisors. The question is no longer whether work will change. The question is how quickly society can adapt. For ordinary people, however, the most noticeable changes may come through everyday technology. Future digital assistants could become astonishingly predictive, not because they can read minds, but because they become exceptionally good at forecasting behavior. By combining advanced artificial intelligence with quantum optimization, future systems may anticipate needs before users express them. Transport arrives before you request it. Calendars reorganize themselves before conflicts appear. Healthcare systems identify risks before symptoms develop. Energy consumption adjusts automatically before costs rise. Technology shifts from reactive to proactive. Machines stop waiting for instructions and begin anticipating intent. The convenience could be extraordinary, but convenience always carries a cost. The greatest challenge of the quantum era may not be technical, it may be philosophical. For centuries, privacy has been intertwined with freedom. The ability to keep information confidential has shaped personal autonomy, commerce, politics, and human relationships. Quantum computing threatens many of the assumptions that underpin that privacy. As computational power expands, maintaining secrecy becomes increasingly difficult. Governments, corporations, and citizens are now confronting a question that may define the coming decades. How do we preserve individual freedom in a world where information becomes infinitely more accessible? This challenge has given rise to a new geopolitical concept: quantum sovereignty. Nations are racing to establish control over quantum technologies, quantum secure communications, and the legal frameworks that will govern this emerging reality. The next global competition may not be over oil, manufacturing, or even artificial intelligence. It may be over quantum leadership, because whoever leads the quantum era may help define the rules of the digital world itself. Quantum computing isn't simply another technological upgrade, it's a civilizational transition, a shift from binary certainty to probabilistic possibility, from silicon limitations to quantum potential, from reactive systems to predictive intelligence. It promises extraordinary advances in medicine, energy, transportation, logistics, and artificial intelligence. Yet it also forces humanity to confront difficult questions about security, privacy, power, and control. The future may become more efficient than anything we've ever experienced, but it may also become more transparent than many are prepared to accept. The quantum era is approaching faster than most people realize. And when quantum computing becomes part of everyday life, the world won't simply run faster. It will operate according to entirely different rules. If you enjoyed this exploration of the technologies shaping tomorrow, subscribe to Snobbots for more insights into artificial intelligence, quantum computing, robotics, and the innovations redefining civilization. The future isn't coming, it's already being built. This is Snobbots, where mind meets machine.